Hey, this is the Amateur Logician from amateurlogician.com. I really do hope you are doing well. Together, let's preview the fascinating subject of infinite sets. Now, amazingly and really surprisingly, there's a certain density to infinity. These densities are categorically, or so to speak, quantitatively different. We can classify some infinities as being greater than other infinities. There's a hierarchy of infinities. And this was discovered by the great mathematician and logician George Cantor. Now recall that a set, loosely speaking, is a collection of objects, a collection of things. And we're thinking about the size of a set. It can either be finite, for example, we might have 5 elements or members of a set, or 100, or a billion, or a trillion. There might just be one, or it might be empty. We can have the empty set. Alternatively, the set size might be infinite. For example, consider the set of all natural numbers, or all integers, or all rational numbers, or all real numbers. But that infinity can be subdivided into the countably infinite and the uncountably infinite. And we'll discuss that in a few minutes. The funny nature of infinity actually was somewhat touched upon by Galileo, because we have what's now referred to as Galileo's paradox. Generally, isn't it the case that the part is smaller than the whole? But you can have situations when we're dealing with infinity where this seems not to hold, or at least we have to consider part-to-whole relation in a different way. Now, someone new to logic and philosophy might not realize how the development of analytical philosophy was immersed actually in the development of contemporary mathematics. Questions even concerning non-Euclidean geometry played a big role. Such questions were additionally tied to the consistency of arithmetic itself. Is arithmetic consistent without any contradictions? Now, clearly the development of symbolic logic was really important, both for analytical philosophy and mathematics, but there was more to it than that. Another big area of development dealt with set theory and, in fact, infinite sets. So when thinking about this, let's set the stage a little bit in this brief logic of infinity. Now, doing that, we should think about a function, and let's recall our high school algebra. So a function, let's say from A to B, is a rule that assigns to each element little a, which belongs to big A, exactly one element, f of A, which is an element of big B. We have an input-output relation. You have an input, and with an input, only one output is spit out. We have a relation. The input is the domain of the function. The output is the range of the function. The function f from A to B, where A is the domain and B is the target. And we can have different types of relations here. And this will be important when we consider infinite sets. So one type of relation is the surjective relation. So here, the range of the function f is the entire target. So here is the target B, set B. Here is our domain, set A. There is a rule that assigns how we move from A to B. That's the function. And notice that A is an output and B is an output. So the input X, for example, gives us the output A. The input Y, for example, gives us the output B. The input Z, for example, gives us the output A. Everything in B is reached. So we have a surjective relation in this function. Another possibility is that we can have an injective relation. So if every element of B has at most one input that gets us there, at most one, maybe none. So notice again the target B. So A has only one input getting to it. B has only one input getting to it. C has none, but that's okay. And D has only one input getting to it. So that's an injective relation. But notice that in this case, this particular function is not surjective because C is not hit by any input. And finally, we can have a bijective relation. And a bijective relation is both surjective and injective. Okay, so if you notice the function from A to B, everything is reached in B, and every element has at most one input that gets us there. We have this one-to-one correspondence. Input X, you get the output A. Input Y, you get the output B. Input Z, you get the output C. So there's a bijective relation. And we're going to utilize this knowledge to think about infinite sets. Because one of the things George Cantor thought about is a mapping, a one-to-one mapping or homomorphism, where we can link up infinite sets to each other through this bijective relation. Consider Galileo's paradox. So we have two sets here. We have the natural numbers. These are like the counting numbers. So 1, 2, 3, 4, 5, all the way to infinity. And then we have perfect squares. So 1 squared is 1, 2 squared is 4, 3 squared is 9, etc. So we have 1, 4, 9, 16, etc., all the way to infinity. Now there's something Galileo noticed. On the one hand, that the set of squares is a proper subset of the natural numbers. Okay, so we have S as a subset, a proper subset of n. So every member of S belongs to n. So 1, 4, 9, 16, etc. Those are all natural numbers. On the other hand, there are natural numbers that are not perfect squares. For example, the number 3 is a natural number. It belongs to n, but it does not belong to S. However, even though one set is a proper subset of another, that is to say, S is a part of n, but not vice versa, they have an equal size because we can match up all the numbers. In other words, we can match up this 1 with this 1, this 2 with this 4, this 3 with this 9, this 4 with this 16, etc. to infinity. Notice this bijective relation from the natural numbers to the squares. And that means that they have the same cardinality, these two sets. Or in other words, when we're saying cardinality, we're thinking about the size. The size of both sets is equal. What's paradoxical is that one is a proper subset of the other, but they have equal size. Because in general, that doesn't hold. If we're thinking about finite sets, that definitely will not hold. Like for example, if we have, let's say the set X is equal to 1, 2, 3, and the set Y is equal to, 1 and 2, well, Y is a proper subset of X, but they don't have the same cardinality because X obviously has 3 members and Y only has 2 members. So in general, if one is a proper subset of the other, one's going to be bigger than the other, but when it comes to infinity, that is not the case. Both are infinite sets. However, some infinities are in a certain sense bigger than other infinities. Consider the natural numbers and the integers. So the natural numbers, the counting numbers, 1, 2, 3, 4, etc., are a proper subset of the integers. And the integers include the negative whole numbers, the positive whole numbers, and 0. But even though the natural numbers are a proper subset of the integers, they have the same cardinality, right? Because every natural number can get paired with an integer. So we can go from 1 to 0, 2 to 1, 3 with negative 1. So we'll just bounce around there with the negatives. 4 goes with 2. 5 can go with negative 2, etc. So again, we have this bijective relation, this one-to-one correspondence, and so we have the same cardinality. Again, even though one is a proper subset of the other. Now, importantly, we will say that something is countably infinite if it has the same cardinality as the natural numbers. So we have this idea of countably infinite. Do we have uncountably infinite? That's the question. But what about the rational numbers? So there's an awful lot of them, right? You have the fractions. So 1, 1 over 2, 1 over 3, 1 over 4, etc. Are the rational numbers countable or uncountable? So one of the things that Cantor discovered is that, in fact, the rational numbers are countably infinite. And this brings his diagonalization argument. So what we're going to do is this. We're going to think about just the positive rational numbers for now, because it's easier. And we're going to make this table. So we have 1, 2, 3, 4, 5, etc. And this is going to represent the numerator of the number. And then we have 1, 2, 3, 4, and 5, where these numbers will represent the denominator. And we're just going to have the numerator over the denominator. So 1 over 1, 2 over 1, 3 over 1, 4 over 1, 5 over 1, etc., etc. We'll have 1 over 2, 2 over 2, 3 over 2, 4 over 2, 5 over 2, etc., etc. We'll have 1 over 3, 2 over 3, 3 over 3, 4 over 3, 5 over 3, etc., etc. 1 over 4, 2 over 4, 3 over 4, 4 over 4, 5 over 4, etc., etc. 1 over 5, 2 over 5, 3 over 5, 4 over 5, 5 over 5, etc., etc. Now what we're going to do now is cross out the redundancies. So we already have a 1, so let's get rid of 2 over 2, 3 over 3, 4 over 4, 5 over 5, etc. We have a 2, so let's get rid of 4 over 2. We have a 1/2 already, so let's get rid of 2 over 4. And we're still going to make this one-to-one kind of argument. We're going to create this bijection, and we're just going to kind of spiral around this in this way. So we have 1 over 1, in other words, just 1. We have the 2, we have the 1/2, we have the 1/3. We skip over the 2 over 2 to go to the 3 over 1, in other words, 3, to the 4, to the 3 over the 2, to the 2 over the 3, to the 1/4, to the 1/5, skip over, skip over, skip over, skip over to the 5 over 1. And we keep on spiraling around this infinite table. We can match up the natural numbers with these numbers. So we can say, hey, 1 goes with 1, 2 goes with 2, 3 goes with 1/2, 4 goes with 1/3, 5 goes with 3 over 1, etc., etc. And then all we have to do then to just expand this argument to think about all rational numbers, not just positive rational numbers, is just flip the signs, plus and minus. So we match up this giant kind of snake-like pattern, so to speak, and then we get this bijective relation. So that means that the rational numbers are countably infinite. Even though it seems like, hey, there's a ton of fractions out there, so you would think prima facie that this infinity should be more, right? Or perhaps it would be more. But then, so far, it seems like, okay, all these infinities are really the same size, the same cardinality, so there's nothing much to this, it seems. But then we jump into the real numbers, and then we fall into difficulties, where we can't match it up, where it's actually impossible to match the natural numbers to the real numbers. And if you try to assume you can match them up, you get a contradiction. So you have a proof by contradiction, proving that the real numbers are in fact not countably infinite. And there's a certain sense in which that infinity of the real numbers is greater than these countably infinite sets. So we're thinking about the real numbers. And that would include things like, hey, the square root of 2. Is it even possible to match the real numbers up to the natural numbers? Both are infinite in size, so perhaps we can do that. But in fact, you can't. The density is just at a different level when we come to the real numbers. So in fact, what we can say is that the interval just from 0 to 1 is uncountable. There's a certain sense in which just the numbers between 0 and 1, that is, contains more density at a radically different level than all the natural numbers. And we're going to do this proof by a contradiction. So we have proof by contradiction. So we're just going to suppose that there is a bijection from the natural numbers to the reals on the interval 0 to 1. Can we make this mapping? So let's say we have the natural numbers, and then we have the real numbers. We want to see if we can match them up. So we get 1 to some number. Let's think of some real number x, and that's just equal to 0 point digit 1, digit 2, digit 3, etc. to infinity. For example, consider 0.1, 1/10. So that would just be equal to 0.1, 0, with a 0 repeating. So right now, we're just supposing that we can make this bijection. So we have the natural numbers to the real numbers. We can do this mapping, this homomorphism. So 1, let's say, goes with 0.34288. Let's say 2 goes with 0.00122. Let's say 3 goes with 0.87776. Let's say 4 goes with 0.84222. And let's say that 5 goes with 0.00001. And so on and so forth. We're just assuming that this is the case, that we can do this. Let's think of another number, and we're going to call this number b. Think about number 1 paired with that 0.34288. We'll think about that first digit. And with the second number, we'll think about the second digit there. The third number, that third digit there. The fourth, the fourth digit there. The fifth digit there. And what we're going to do is just add 1 to each of those digits to create a new number b. So in other words, the 3 goes to the 4, the 0 to the 1, the 7 to the 8, the 2 to the 3, the 1 to the 2. So we create a new number, so 0.41832. So this is our new number b. And the question is b on the list? It should be. It will be on the list insofar as the real numbers are countably infinite. But think about it. b is not the first number, right? Because it differs with that number in the first digit. We have that 4 there. This has a 3 there. So it can't be the first number. It's not going to be the second number on the list because the second number, second digit, is different than b's second digit. But maybe it's the 100th number on the list or the billionth number on the list. Could it be the billionth number on the list? Well, no, it can't be, because the billionth digit is different than b's billionth digit. So b, this number, we constructed it in such a way to disagree with every number on that list by at least one digit. Purposefully, we've made sure that b will not be on that list. It is absolutely impossible. So, because b is not on the list, that contradicts the assumption. So therefore, we have something that's not countable. and we have a proof by contradiction. Now, I don't know about you, but that's pretty cool. But at the same time, it makes sense that the density between 0 and 1, there's no way you could pair that up with the natural numbers. That density is at a radically different level than the natural numbers. So because of that, we can say that the real numbers are really greater than the natural numbers. Both are infinite in size, they're sets, right? The set of all real numbers, the set of all natural numbers, but the density of the real numbers is at a different level. That infinity is greater than the infinity of the natural numbers. So this has been a preview or introduction to the logic of infinity, or I should say infinities plural. I am the Amateur Logician, of course, from amateurlogician.com. If you enjoyed this video, please consider giving it a like. I would appreciate it. You can sign up to my newsletter if you visit my website. And you can also follow me on X, formerly known as Twitter. If you have any comments, please feel free to leave them below. I do read them, and I try to reply to them when I'm able to. In any case, thanks for watching. Good luck to you, and be well.